This is the extraterrestrial power plant evolutionary design. The fact that out there is no convection cooling. The wind is not blowing because there is no wind. The cooling there is by radiation. So the so-called ambient is not the cold air. The ambient is the cold sky. You still have a heat source, which is the sun. The power plant has a collector that receives the net heat current from the sun. That's called Q dot H. H from hot. The collector has the surface A sub H and the temperature T sub H. And the power plant has a second surface called radiator that rejects heat to the cold sky. That second heat current is called Q dot L. And the radiator has the surface A sub L and temperature T sub L. We don't know these temperatures. We know the areas, meaning the sizes. We know them painfully, really, really well, because to hurl mass in space is very expensive. So the sum of those two things is what matters, and it is fixed by your budget. Now, the heat current comes from the sun, which is, when seen from the top end of the power plant. By the way, here's the power plant again. It is assumed to operate reversibly. It produces power called W dot. And you get the idea that I'm not telling you anything new. But at the hot end, the heating comes by thermal radiation from this hot object called sun of temperature Ts. The sun, of course, is spreading its radiative input in all directions available to it. The collector intercepts only it's called a pencil of rays. And then the same collector, being now hot, called TH, sends its rays in all directions of the solid angle seen from its level. In other words, if you take a course in heat transfer, you arrive at a so-called enclosure. Enclosure, the surfaces of which are not isothermal. There's a hot one, a not so hot one, and then a very cold one called the cold sky, or the rest of the universe, or say 3 degrees Kelvin. So this is 3K. This other one, the collector temperature, is once again unknown. It is a variable. At the other end is the same sort of radiative heat transfer phenomenon, except that there is no sun at the cold end. The radiator sees nothing but the cold sky. In other words, the radiator radiates this way. Of course, I told you already, the collector was also radiating back. this arrow, the one called the Q dot H, is the net heat current that penetrates the collector. In other words, the difference between what arrives and what leaves. What arrives is the so-called pencil of rays. What leaves is shown in red. The difference between the two is positive and entering the top end of the power plant. Now, the mathematics of it is, as I said, relies on the knowledge of radiative heat transfer. I'll just write these a few statements on the blackboard. Those of you who do not have the background, that's okay. These equations that you'll see next, there are very few, there are only about 3 of them, are in the textbook. So Q dot H is equal to what arrives, namely a factor proportional to the size of the collector, and then a dimensionless factor called the view factor, HS, meaning the view factor between the collector surface and the surface, the visible surface of the solar disk. And then the Stefan Boltzmann constant sigma, and then T S to power 4 minus TH to power 4. So this factor accounts for arriving heat current. And then from it, I subtract the departing heat current shown in red, namely minus, again, proportional to the collector surface. There is a view factor between the hot surface and the cold sky. And then TH to power 4 minus T infinity to power 4. There is a theorem in this domain that after you prove it, you discover that the sum of these two view factors, FHS plus FH infinity equals 1. In other words, as you look from, for example, this location, you can see the whole. The whole is the so-called hemisphere, which represents that, and contributing to that ability to see are these two objects, the sun and the rest of your field of viewing. And that means that you have only one F to worry about here. We'll use this FHS. And another simplification is that 3 degrees Kelvin to power 4 is negligible compared with any other temperature that's in the hundreds to power 4. So therefore, we neglect that. And that allows us to simplify this expression for the net heat current entering the collector as sigma AH. And then at the cold end, meaning the radiator, the only surface that is seen from the radiator is the cold sky, and the formula for the heat current. And by the way, the view factor between radiator and the cold sky is 1, so I don't even write it, where I neglect the small one, T infinity to power 4. And then finally, we're not interested in the Q's here. We're interested in W dot. I teach myself not to say the word finally, okay? So the next step, the door open to the future, is the formula for the power that is provided by this contraption. Obviously, it is, as usual, Q dot H times the Carnot efficiency. The first move I make is to contemplate the manner in which size is allocated between the hot end and the cold end. So I invent the degree of freedom called X, which is dimensionless for the size at the hot end divided by the total size, which of course means 1 minus X equals AL over A. So X is 1 degree of freedom. But there's another degree of freedom, which is the location of this engine on the temperature scale in space. In space. Meaning it could be small and big, but where is it? Is it high in temperature or low in temperature? So there's a second degree of freedom accounting for the temperature location of the whole drawing, and that one is called zeta in the textbook. It stands for the view factor HF sub HS times the ratio sun temperature, collector temperature to power 4. So we have 2 degrees of freedom. If you do not see that, if you do not have a feel for the existence of your double power to trumpet the discovery of this design, then the mathematical expression for W will tell you what those 2 degrees of freedom are. And so here's the mathematical expression in dimensionless form, W dot, meaning after you make all the substitutions, divided by sigma total area F HS and sun temperature to power 4, all of that equals X times 1 minus 1 over zeta. And then there is a ranking of brackets in algebra. The lowest rank is the round bracket. The next higher is the square bracket. And the third higher is the accolade, or the so-called curly bracket. And so, so the expression is a long sausage, which goes like this: 1 minus, and then square bracket x1 divided by 1 minus x, and then zeta minus 1 in round brackets. The square brackets are raised to power 1/3, and then you close the accolade. And here you see that the new W dot tilde is a function of 2 degrees of freedom, X and zeta. We are really clever, we, Homo sapiens. We see 2-dimensional images. The field of vision is you're watching a movie that's on a flat screen. That's what we observe. The world is flat. We see interesting stuff on a horizontal stage, wide stage, which is of course not the case. Everything is 3-dimensional. Not only that, but it's moving changing in time. So for the complications, we are endowed with imagination and with memory, and with the ability to kind of change our opinion. That's even more important. Let me come back here and tell you what to do when you reach this stage in the argument. Here's the function. You can do this analytically and plot it with respect to x, meaning 1 degree of freedom, after you assumed zeta fixed. You can plot it, or you can simply treat zeta as a constant and then take the first derivative of the function with respect to x. And you discover that this w dot is non-monotonic with respect to x, meaning it has, you've actually discovered it has a maximum for, meaning one maximum. You can call it x optimum for the assumed zeta. If you don't like x, you can vary zeta and fix x. Let me act as if I prefer the second option. So this is x fixed, and zeta varies on the abscissa, and I discover the same thing. I can play this game to convince myself that both degrees of freedom should be of interest to me, meaning they are potentially useful in locating the design that is the most promising, the so-called belly button. Another way is not to go from left to right, but to keep doing the first one for additional values of zeta. This way. So we repeat this drawing for one value of zeta, call it zeta 1. So this is w dot w and x. And then we change the zeta, and we get another curve, meaning the peak of it climbs up, and then we change zeta again and get another curve. The peak goes there, and of course we're getting drunk here. We keep drinking, you see, and then surprise, the next constant zeta curves are sliding downward. And if this was this peak was the maximum or the optimum, then the peaks, 1 point corresponding to 1 zeta, the peaks describe a curve of their own. Which is the peak, the curve of the optima. And the curve of the optima itself has a peak, which is represents the highest of the peaks. This highest peak is the maximum of the maxima, also known as maximum maximorum. Corresponding to it are two values, the optimal x and the optimal zeta. In other words, if you this is name dropping, this Latin stuff. Maximum maximorum could also be at the next time at the drinking party when those around you are more gullible than you are. You say optimum optimorum. You know, see what they say. For the situation at hand, which is this power plant in space being driven by the sun. I already wrote what to substitute in these definitions, meaning in definition of zeta, and namely Ts. The solar temperature is 5762 Kelvin, and if you make that substitution, then at this optimal design in blue, the optimal collector temperature is 5174 FHS 214. That's a number of Kelvin degrees. By the way, the value of this view factor is 10 to minus 4, which means that this temperature, the one that corresponds to the blue design, to the peak of the blue design, is about 520 Kelvin. And correspondingly, at the cold end, the temperature is roughly 340 Kelvin. But the key point when it comes to hardware is the value. By the way, these values, in fact, I should have written them first. The optimal value of psi, of zeta, is 1.538. And for the size allocation fraction, that value is 0.35. So you see, from the total inventory of size, you allocate 1/3 to the hot end and 2/3 to the cold end. And which shows you that, well, I erased the drawing. I drew the power plant this way with AH here and AL here in a way to show you that the hot end is half the size of the cold end. All right. So with this, I made 2 points. Not only the taking Carnot's idea of heat engine into space, or replacing the fire from coal, replacing it with the sun, but I showed you that one idea, which is designed from the freedom to change features, including size, design is in your grasp if you know the fundamentals.